Okay, it's recording. But it will be easier for me to respond. Please don't turn your videos. At least I can see your faces that you don't understand anything I'm saying, or you do understand everything I'm saying. Let's see. So semantic segmentation. In my last lecture yesterday, while you were asleep, and you haven't watched it apparently, I was talking about semantic segmentation problem. And okay, one of my goals is for you to understand and not be scared when you hear at the interview or in the paper terms like fully convolutional neural network, right? Fully convolutional. The first time I heard it, I was like, what is that? The same happened to me, by the way, with highway networks. I saw them, I was there when they were presented at the conference, and I was like, oh, this is too complicated. I just can't see what it is. Highway, and I couldn't get it. Very simple. The ideas, all of the ideas are simple if when you can sort of dig them up. Let's try that. So we've seen all of the components in this diagram before. Our fully convolutional neural network, and you're time travelers, you're going backwards in time, you will watch my lecture on fully convolutional neural network. The original fully convolutional neural network looked like that. And I think it was published around 2014. Start with an image, convolve again, downsample, max pooling or something. Go through another layer, do a convolution followed by downsampling, max pooling. This one has specific structure. It goes through two convolutional layers before it does max pooling, but you can just interleave each layer with max pooling operation, and then this will look more conical, right? It will reduce in dimension with each step. That's what's happening here. We're reducing dimension, sort of creating a bottleneck, forcing the network to learn more and distilling that information. But then at this last step, fully convolutional network applied an upsampling operation, which I do explain in the building blocks in the first video. So this upsampling creates an output of the same dimension as the input. So you have correspondence of your label or a segmentation sample with your pixel. For each pixel, there is a segmentation sample. Quite simple. The only building block was convolution and max pooling, but then upsampling. 3 building blocks from the first lecture.
Isn't this a typical autoencoder?
No, there is no autoencoding here. The training is actually supervised. You have a segmentation. The autoencoder exploits the same property about any models, is creating a bottleneck. We want to create, well, there is a guy, Naftali Tishby in Israel, who actually has a theory, it's called information bottleneck theory. And sort of a vague statement is that in order to learn anything, you have to do compression. So you have to represent in lower dimensional space in order to learn only useful parts of your data space. Autoencoder, if you draw it as this hourglass and this is the representation, this is not autoencoder. We get our final representation somewhere here and then we upsample it. But autoencoder, even the name is talking about just specific type of training. Autoencoder is an unsupervised model, or self-supervised rather. That's how we decided to call those models, because it's trained in a supervised backprop manner, but the error is reconstruction error. You want to reconstruct the input, even though it was passed through a bottleneck through low rank representation. So you want to find a low rank representation of the input such that it's informative about recreating that input. Like our low rank representation of our speech is our text.
So, I mean, at least in this scenario, if we use our input that we are passing to the architecture as our labels, like the final needed output, it becomes an autoencoder. At least the architecture is in line with the autoencoder. That's what I was asking.
It is becoming a model that is trained in your description. It's a model that is trained to minimize reconstruction error. So if this is X and this is reconstructed X, and you train it to minimize this error, let's take L2, then you're minimizing reconstruction error. This is the reconstruction error. Autoencoder, yeah, you can call it autoencoder. It's just a name, right? But because it's just a name, there is an established way of using that name. So don't call the fully convolutional neural networks autoencoder in public, or people will think, even though you understand everything, but people think you don't know what you're talking about. It needs some explanation. So if you don't care about people's opinion, though, you can do whatever. It's just fine. But yes, you're absolutely right. There is some similarity, but similarity is rather here in the reconstruction error. If you train it with reconstruction error in mind. Good. Let's go back to the unit. So if you look at this encoder that telescopes in, compresses the image representation here. It's practically that part of the fully convolutional network of 2013. What the fully convolution, and then you get here. This layer and that layer here are practically the same. Then what they did in 2014, they upsampled. So they convolved with a filter. Upsampling or upconvolution is clear, right? If you have questions, ask me now. Otherwise, you lost your chance. Okay, moving on. What UNet people did, Ronenberg. MICAE is a good conference for medical imaging. This paper is cited more than 13,000 times now. Yes, the network, the model turned out to be so powerful that people in medical field especially are using it everywhere, publishing it all over the place, making a tweak or another tweak and publishing under a different name. There are gazillion variants of UNet. Why it's called U? Because of the shape. It's like a U sign. That's it. There is no magic there. So instead of just upsampling in one step, UNet does, yeah, let's leave it here. UNet does step-by-step upsampling using the same dimensions as it was downsampling or max pooling as it was compressing. Because it's using the same dimension, so dimension of the layer 4.2 is the same as this upsampling dimension here in layer 6.0. And then you can add skip connections. You can simply, like ResNet did, watch the skip connection part, very important part as well in all of the deep learning, not just the convolutional. That's my second video. 30 minutes at speed 2.0 is 15 minutes and you're done. You're now a professional. So don't hesitate. So, but now we added those skip connections. And what we're doing with the skip connections, that we're saying, okay, we're upsampling this essential representation of the image that was useful in fully connected network. But we're augmenting the information. So if we cut this and try to upsample even step by step, then eventually we're losing the information about fine resolution. Those skip connections are adding the fine resolution information about our image representation, input image representation. So UNet, good model. But as with anything, there's a price. Let's take a typical UNet that this is one very specific. We used it for brain imaging problem I will describe in this. 23,000 parameters. 23 million parameters. It's the model weighs about just the model, not activations, not anything. Save the parameters to disk. It will be about 2.5 gigabytes. So try to share this model with your friend. Try to share a few models with your friends. So it becomes difficult. Very successful model, works really well. It's trainable, but we didn't like it. So let's see. I was thinking, let me look at it. I thought I rearranged the task. Okay, well, let me define the problem first. So we're working with the brain and also have a segmentation task, and we want to segment the three-dimensional brain into gray, yellow. Yeah, yellow is gray. Just do the mapping internal, and red is white. So we want to do gray and white matter segmentation of the brain, and in one task. This is task one. And in another task, we want to segment the brain into functional regions, like visual cortex, motor cortex, left motor cortex, right motor cortex. There are 105 different functional regions. This is to Nikhil's question. How do we get people, and remember, those are 256 cubes. How do we get people to sit down and label this for us enough so that we can get usable data so that we can train a model? Well, very difficult, we couldn't. So what we did instead, we took a normal signal processing approach. And that's what people are doing now. You just take an existing tool, which is not perfect, it's not a human, but it's an algorithm that takes 10 hours to do all of that labeling and segmentation. It's not perfect, it makes mistakes, I'll show some of them. But we use this output as our teacher. So if you can come up with a coarse, Nihil, if you can come up with a coarse way to label your cats by using just objective methods like signal processing, edge detection, and Sobel filters and things like that, that could work potentially. This one is, of course, much more complicated. People have spent years and years. A team at Massachusetts General Hospital developed that tool. So it was, all right, it is quite good. People are using it as industry standard. But we also were not happy with the size of the model. The 2.5 gigabytes is very hard for us when we're building a system that trains the model across institutions. So sending a model of 2.5 gigabytes each time we do a parameter update is impossible. Dilated convolutions were of help. This is the model. All of the layers have exactly the same size. And all of the filters are also, I'll show you a table, they're 3 by 3, regardless of the layer. So you're not adding the parameters, you're seeing more, you're dilating with each layer, your dilation coefficient, dilating more and more, not just by adding one, but next time you add two in between, you increase the holes. By the way, dilated convolution is often called I think I'm spelling it right. So basically in French, something blah, 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 French word. Basically convolution with holes, just as simple as that. And in English, we took it back as atros, just without translation. But it's a convolution with holes. Convolution followed by ReLU, batch norm, dropout, 3D. All of the layers are exactly the same. Imagine this. If it was an image, a 2D image, the model would just look exactly like that. All of the layers, all of the outputs are the same dimension, at least until you come down to the output layer where your labels are. But what people usually do, instead of having one output layer and label the images 1, 2, and 3 classes, you just have one binary mask as an output per class. And then you can softmax on this dimension. And for each pixel, just softmax decide which class this particular pixel belongs to, if you're going to use that in practice. What did we get with that. Yeah, all of them are just 3x3 kernels. And this is 3D. So we're convolving in 3D. Number of parameters is 72,000. 600 kilobytes versus 2 gigabytes model. The accuracy and performance is better, and it's a faster model. It's lightweight. There is a huge problem though. No free lunch. Remember, nothing is for free, because it's a 3D model. Because our dimension never changes. We always have the same dimension for each layer. Our activations, our channels are always the size of original image. So this model requires more memory in GPU, even though the number of parameters are 300 times lower. Because of the activations, because of backprop, at each step, we compute activation in one layer, and we need to store it in order to compute backpropagation. We compute activation in the next layer, and we need to store it. So it still works faster. Another trick, practical trick that you probably know. So we have a full brain, and the full brain doesn't fit in the memory because of that problem. UNet cannot apply the algorithm on the full brain. So what we do, we sample subcubes randomly. We take center of mass of the brain and align a Gaussian distribution here, and sample some subcubes according to this Gaussian distribution and train on these subcubes. On the prediction time, we again sample them and do model averaging. Just by voting, majority voting, what will this pixel be? It's still under 1 minute. Original model, the teacher that we trained it on, and that's how UNet model is also trained. That's how people do that. Takes about 8 hours for the job, and those models take less than a minute for the job to label the whole brain, the new brain. Yeah, ground truth. Well, ground truth, the teacher is not the ground truth. It's not human label, it's the automated label, and this is MeshNet predictions generations. Interesting parts, that's back to UniHill. Sometimes the model, our model, that was trained on this teacher is better than the teacher. The teacher makes mistakes. The model was trained on, like, look, there is this structure in the brain which is called corpus callosum. Free surfer misses it here. Our model gets it. But wait a second, we just learned from this model. This is out of sample, this is testing data. But we learned from this model and we're better than this model. Same here, we're better than the original model. Sometimes we make mistakes as well, like this is part of the skull and our model got them. It shouldn't have gotten them. But this is surprising. So you need to know key information or key insight about deep learning models, that they are statistical models, and when you're training them with incorrect labels, and if those incorrect labels are not systematic, the model learns to average over the non-systematic errors. So you can have non-systematic errors in your training data set. It doesn't have to be absolutely perfect, as long as you have enough data to overweigh those non-systematic errors. If the errors are systematic, the model will learn to predict them. If say your teacher, your labels are always wrong in one particular place on one particular type of inputs, then the model will learn to do that. But don't be afraid of noisy labels. That's a useful insight. As with anything in deep learning, the same here, are engineering diagrams. If you have one input to your model, it's very easy to have 3 inputs to your model simultaneously. Multimodal learning from different classes of images, 3 classes, T1, T1IR, and FLAIR. We just learn as well as, well, get better accuracy for free without inventing. Think about PCA. How do you do multimodal PCA? You have to click, your data is differently scaled, and has different dimensions. You can't do simultaneous PCA of different modalities, speech and say vision, view of your lips, which move when you speak. Yet in deep learning models and segmentation models specifically, you can just easily combine everything in engineering way. Another interesting part about superhuman performance, people are faulty. We get tired very quickly. And we're limited in our senses. So a human expert labeled this image. And our prediction is better than human expert. Why is that? Well, human expert has to look at three-dimensional representations simultaneously and has to look somehow in 3D, because if you go slice by slice and you go in this direction, you may miss that your slices don't match in this, in the other and Y direction. And that's what probably the humans done, that mistake. The slices just didn't add up. They all merged together, despite the ground truth was disconnected. So that's important part. And of course, this is just measurements of running time. The top signal UNet has more parameters. It's computationally more intensive, so it takes more time. Well, this is number of subvolumes for us, how many subvolumes we take to make a prediction about a single pixel. So the point of this, presenting you the model that my group developed and comparing it to existing model, is to show you a creative use of two techniques. Skip connections for UNet were instrumental. 13,000 citations, as I mentioned, right? And for us, for MeshNet, we didn't use any skip connections, but we used dilated. We didn't find improvements with skip connections in our case, but we found that dilation was really instrumental in achieving our goals. So if you are comfortable with the building blocks that I presented in the previous part, you will be able to build your own models. And what you see on the videos is just a slice-by-slice demonstration of the teacher and the result when the model predicts 100 classes of different labeling. And back to a regional question, Susan. If you're looking, I can't pause this unfortunately, but if you're looking here in the top of the brain or in the back of the brain, the gray matter and white matter and the folds are essentially the same. How do you know that this is visual cortex and this is frontal lobe cortex without having any additional information? So if you have a faintest idea, like a very blurred, that you are now looking in the front of the brain, then the model knows, well, in the front of the brain, I never see the visual cortex. So that hypothesis is refuted. And the same in the back. So it's enough to have a blurry idea of where you are in order to improve your performance greatly and have a few parameters. So that's a very good technique. Okay, I think I will stop the recording here if I manage.